In this lecture, let's look at this example. We want to sketch a rational function of a given f of x. By just looking at this rational function, let's make a few notes. So we notice that in the numerator, we have a repeated linear factor and a linear factor. So in the numerator, it is a polynomial of degree 3. In the denominator, we have 3 different linear factors. So in the denominator, it is a polynomial of degree 3. Let's find the roots of the polynomial functions in the numerator and the denominator. Let's call the polynomial function in the numerator p of x. P of x has roots at x equals to 1 and x equals to -2, where the x equals to 1 is the repeated linear factor. How about the polynomial function in the denominator? Let's call this function q of x. Then q of x has roots at x equals to 1, x equals to -1, and x equals to 2. And remember that a rational function, p of x divided by q of x, has roots at the root of p of x. And if p of x and q of x have the same root, then the root is a whole if the multiplicity in p of x is greater than q of x. Otherwise, that will not be a root. So just from these two information, x equals to -2 is a root for p of x and is not a root for q of x. So the function has a root at x equals to -2. P of x also has a root at x equals to 1. However, q of x has the same root. Then we have to compare their multiplicity. In p of x, the linear factor x minus 1, its multiplicity is 2, but the 1 in q of x is only 1. So this linear factor in the numerator is greater than the multiplicity in the denominator, which means at x equals to 1, it is a whole. Then the other two roots in the q of x. Since the function is not defined when the denominator equals to 0, that means we have vertical asymptotes at x equals to -1 and at x equals to 2. How about the horizontal asymptote? We noted from before that q of x and p of x have the same degree. They are both degree of 3. So the horizontal asymptote is simply the leading coefficient. The function has a horizontal asymptote at y equals to an divided by bn, the leading coefficient. From p of x, the an, the leading coefficient, is 2. In the denominator, in q of x, its leading term is 1. So the horizontal asymptote is at y equals to 2. What else can we get from this function if we want to sketch the function? We can also find its y-intercept. To find the y-intercept, we substitute x equals to 0 into the function. We get 2 times -1 squared times 2 divided by -1 times 1 times -2, which equals to 2. So the y-intercept is at 0 and 2. Then let's find the intervals where the function is positive and intervals where the function is negative. Let's set up a sign table. So the axis is for x values. From before, we already found that there's a vertical asymptote at x equals to -1 and a vertical asymptote at x equals to 2. And we found that at x equals to -2, it is a root, and at x equals to 1, it is a whole. Now we have 5 intervals that I want to find the sign for f of x. So I can substitute any number from each interval into f of x to find the sign of the function. For example, I can substitute -3 and I get a positive y values. So for the interval from -infinity to -2, the function is positive. Then I substitute another number between -2 to -1, for example, -1.5 into the function, and I get a negative value. Then the next interval is between -1 and 1. For example, I substitute 0, and I already found that from the y-intercept, so this interval is positive. And the interval from 1 to 2, for example, I can substitute 1.5 into the function, and I get a negative value. And the last interval, from 2 to infinity, to find its sign, I can substitute any number in this interval, for example 10, and I get a positive y values. Now let's use the information we found to sketch the function. First of all, we can put all the information we have on the graph. We found that there's a horizontal asymptote at y equals to 2, and a vertical asymptote at x equals to -1 and x equals to 2. We also found the roots of the function. It is at x equals to -2. And at x equals to 1, we have a hole. We also found the y-intercept of the function, which is at 0, 2. Then using this information and the sign table we have, let's sketch the function. So for the interval from -infinity to -2, the function is positive, but there's a horizontal asymptote here, so the function must go from here and passes through this root. Then the function goes negative, but never passes the vertical asymptote. So we get the first portion here. Then in the second interval, we found that the function is positive from -1 to 1, and there's a vertical asymptote at x equals to -1. So the function must go from here, passes through the y-intercept, then reach to the hole. Then the function becomes negative, and there's a vertical asymptote at x equals to 2. So we get to this portion of the function. In the last interval, from 2 to infinity, we found that the function is positive. With the vertical and horizontal asymptotes, we know that the function must be in this corner, and it will get closer and closer to the horizontal asymptote as x approaches to infinity. So we get to this portion of the graph. And that is the end of the lecture. In the next lecture, let's look at an example of absolute value function.